Hello everyone and welcome back to the Jamaican Geologist YouTube channel. This is episode 5 in our Geology Foundation series. You may remember in our previous episode that we explored what minerals are and investigated some of the major diagnostic properties. Well, you can consider this a part 2 to our previous episode. Today we are looking at how we organize or classify minerals. Minerals, as with most things in science, are easier to understand when grouped together or classified. They make things easier for the scientist. Here you will start to see the connection between minerals. And minerals are always fun, so let's get into it. So before we start to get granular, let's look at things generally. Generally speaking, how do we classify minerals? Well, there are 4 major ways. The first way is based on composition. Remember in our previous episode, there was a little chemistry. So by composition, I mean chemical composition. The second way we classify minerals is by the use of it, or purpose, use and purpose. How do we use these minerals as human beings in our everyday life? Now, these two sort of mark the difference between academia and industry. However, it must be noted that chemical composition usually determines use and purpose, so the two kind of go hand in hand. Other ways are by formation and visual aesthetics. So from a chemical standpoint, when we get down to it, there are silicates, carbonates, phosphates, sulfates, the oxides and native elements. From a use and purpose standpoint, there are metallic minerals and then there are industrial minerals. And the other major headings like formation and visual aesthetics have fewer subcategories. I will talk about the subcategories of all major groupings in the following segment. Now, before I get into silicates, I believe it is important I share with you that the most common rock forming minerals on Earth are composed of the elements silicon and oxygen. Together they make up about 74% of the Earth's crust. And if you watch the episode on elements closely, you may have noticed this graphic that I shared during that episode. So go watch it if you haven't already. Anyway, the two most abundant elements on the chart are silicon and oxygen. This observation becomes important here. The Oxford Dictionary of Geology and Earth Science defines silicates as the most important and abundant group of rock-forming minerals which can be classified according to the structural arrangement of the fundamental SiO4 tetrahedra, which are the major building blocks of the group. Now, this may sound a little complex and technical to some, so let's break it down a little. We see the words most important and abundant. All right, this is pretty straightforward. So we can say that they are significant and plentiful. In Jamaica, we would say a whole heap of them, or them enough, All right, cool. We also see the words rock forming minerals. So from this, we can say that that most of the rocks on Earth are composed of these minerals in some way, shape, or form. We also see structural arrangement. All right. We have been talking about this in our last 2 episodes on elements and identifying minerals. So we have a good idea of what this is. So we can simply say how the atoms bond and the shapes they produce. Lastly, and this is the more complex but important part, we see the word fundamental SiO4 tetrahedra. All right, we know that fundamental means basic, but what on earth do we mean when we say SiO4 tetrahedra? Well, SiO4 is a compound of two elements. Silicon is the Si, O is the oxygen, and the two most common elements in the Earth's crust, as you saw from our chart previously. All right, so we have most of it covered, but what is tetrahedra? A tetrahedron, the singular form of the word tetrahedra, refers to a solid which has four plane triangular faces. Think of a triangular pyramid structure. One thing that immediately comes to mind is quartz, which I mentioned in the previous episode. And quartz commonly occurs in that sort of shape. And quartz is SiO2, silicon dioxide. Again, we see the elements silicon and oxygen occurring together. Okay, good. So based on the definition we deconstructed, let's put it back together and see if we can make a simplified definition for ourselves to better understand these silicates. Here goes. We can define silicate minerals as the most important and most plentiful rock forming minerals on Earth that are composed primarily of silicon and oxygen and form minerals that are shaped like triangular pyramids. That's the best I could come up with in terms of simplification. I hope it makes sense to all my viewers, and I hope you get it. Okay, so we have a simplified definition now. Let's get a little bit more granular now. Notice that the definition from the Oxford Dictionary of Geology and Earth Sciences says fundamental SiO4 tetrahedra. And I just mentioned quartz being SiO2. Okay, so there are some differences here. Silicates can be grouped based on the ratio of silicon to oxygen. Now, many years ago, I can remember Dr. Thomas Stenman of now blessed memory teaching me this, and I had some challenges remembering this subgroup for exams in my introduction to earth science courses. I used to mix up the ratios all the time and put things in the wrong category. To this day, I still do it sometimes. But don't worry. I checked before recording this video, and I promise the ratios are correct. And I will now share a presentation I prepared for this episode of how the different silicates are shaped, and which is which rate which is based on like the ratio of silicon to oxygen.
So I prepared these drawings myself for this video, and I hope that you, my audience, you really get a picture and appreciation for the silicate minerals. So let's start with the nesosilicates. Uh, these are the most basic type of silicates, and in nesosilicates, the SiO4 tetrahedra they're isolated, and they don't share any oxygen atoms with each other. Think of it as like a single pyramid standing alone. So let me just get my laser pointer here. You can see these little points along the tetrahedra. They represent oxygen. So there's 1, 2, 3, 4 oxygens. And then those oxygens link together with one silica, and the silica is within the structure. The common examples are garnet, topaz, olivine, and zircon. And I know it's a lot to take in terms of the formula, but what I want you to focus on is the SiO4 everywhere. SiO4, SiO4. Once you see that, you know that it is a nesosilicate. So next we have sorosilicates, and it's pretty easy. Again, the ratio is 2 to 7. So there's two two silicons, and 7 oxygens. So let's count them: 1, 2, 3, 4 shared here, 5, 6, 7. That's 7 oxygen, and then each of these have a silicon in the structure. So that's where the two silicas come from. And epidote, Vesuvianite, and lawsonite, those are the ones that have the Si2O7 in their chemistry. The cyclosilicates are similar again. The SiO2 ratio is 1 to 3. So 1 silica, 3 oxygens, and if you count all of these up, you get 18 over 6, and you can cancel it out to get 3 to 1. So it's be 3 oxygens, 1 silica, and then you have beryl, SiO3, and then you also have tourmaline, which has Si6O18, and if you really break it down, you get 1 to 3. Um, these are a little more complex now, so you can't really count the the structure within the group. But basically, this group is divided into two. There's the single chain inosilicates, and these have 1 to 3 in their tetrahedra. And then there are the double chains, and the double chains, they have 2 chains of tetrahedra and are linked together side by side. And you can see within the chemistry, if you really break these down, you get 4 to 11. If you break this, this is pretty straightforward. If you break this down, 2 to 6 is 1 to 3, and 2 to 6 is 1 to 3. So it's pretty straightforward. The phyllosilicates now, or phyllosilicates, I should say. These are sheet silicates, and the tetrahedra are connected by flat sheets. They tend to be soft and have a flaky texture like layers of mica. And phyllo means leaf, so think of this group as a leaf group, or leafy layers, And even though the formula looks complex for muscovite and biotite, the tetrahedra sheets where 4 tetrahedra linked together share oxygen atoms, and because of this sharing, the overall silicon to oxygen ratio simplifies to 2 to 5, and this is exactly what we expect. So what happens here is that you can see Si4O10, you cancel this down, you get 2 to 5. SiO2, Si2O5, that's 2 to 5. But here, this doesn't make sense on the surface. But because of the sharing of the different oxygen ratios, it's a little more complex in terms of the network. But overall, it will add up to 2 to 5. And then I think this is the final one. This is the tectosilicates. This is a ratio of 1 to 2. It's pretty simple in terms of the ratio, but really complex in terms of the structure. Each SiO4 tetrahedra shares all 4 oxygen atoms with neighbors, forming a strong 3D kind of framework. And tectosilicates form the backbone, or most of the minerals in the Earth's crust. So a lot of SiO2 exists in nature. And of course, the most common is quartz. But so here is what I want you to remember. Firstly, the silicate group is classified based on how their SiO4 tetrahedra are arranged. And as we go from isolated tetrahedra to full 3D frameworks, the silicon to oxygen ratio changes. And finally, the more connected the tetrahedra, the more stable and common the structure tends to be in nature. So, like quartz, for example, when it becomes 3D, you see more quartz in nature.
Okay, so all these different subgroups and their structures may sound like a lot, but the key aspect I want a general sort of audience to take away from all of it is this: the silicate group has minerals that are chiefly defined by their composition of silicon and oxygen. The ratio of silicon to oxygen determines the category, and perhaps the most common and important is quartz, which is SiO2. And in Jamaica, silicates are what the semi-precious minerals in some of our rivers are composed of. Additionally, quartz is what makes up the silica sand that occurs in parts of southern Jamaica like South St. Elizabeth. I promise the other groups of minerals I'm about to talk about are not as complicated and intricate as the silicates, but that doesn't mean that they are not interesting or important. All right, let's talk about carbonates now. Carbonates are important to many sedimentary rocks like limestone and metamorphic rocks like marble. The most common mineral is calcite or calcium carbonate, and this is what makes up the rock limestone. But there is also aragonite, which has the same chemical formula as calcite, which is CaCO3. These are known as mineral polymorphs. In addition to calcite and aragonite, there is also dolomite. Dolomite is kind of like calcite, but there is magnesium in the equation, so it is considered a calcium magnesium carbonate. I must note here that there is dolomite in Jamaica, but most localities in the island are not a full-blown dolomite, but something called dolomitic limestone. I will get into that in future videos. Outside of the usual calcite, aragonite, and dolomite, there are other carbonates too, which some textbooks sometimes refuse to acknowledge. There is iron carbonate in the form of the mineral siderite. There is magnesium carbonate in the form of the mineral magnesite, not to be confused with magnetite, which I discussed in my previous video. Even malachite and azurite, which also fall in other categories, can be considered carbonates based on their chemical composition. The key takeaway here is that calcium carbonate is the most common type of carbonate, but there are others too which we should not overlook. Once a mineral has CO3, whether it's CaCO3, MgCO3, or Cu2CO3, OH2, it is a carbonate mineral. All right, phosphate time now. So you may have heard of these, especially as it relates to fertilizers. They are a group of minerals that contain the phosphate ion as the main part of their structure. Some common phosphate minerals are apatite, turquoise, fluoroapatite, monazite, and pyromorphite. Some weird sounding names, right? But I also want to share this fact, especially in the Jamaican context. I will share an excerpt from the Mineral Resources of Jamaica. It reads as follows, and I quote: "The innumerable caves in the tertiary limestones of Jamaica have been inhabited by colonies of bats probably for thousands of years, and their excrement has accumulated on the cave floors, often to considerable thicknesses. The phosphate contain or the phosphate content of the guano has been fixed by the cave marl and residual products of limestone solution to form marley and or aluminous phosphates, and in some cases the underlying limestone had acquired a tricalcium phosphate skin following attack by the phosphatic solutions. Accumulations of bird guano are present on the Pedro and Morant Keys off the south coast of the island. End quote. Okay, so let's break down what Fenton said in the Mineral Resources of Jamaica. Generally, many of the caves in Jamaica are inhabited by bats for thousands of years. The bat guano accumulates on the cave floors and builds up into layers. Then there is a chemical reaction between the calcium carbonate in the limestone of the cave and the phosphatic acid from the bat droppings. So the two reactants in the formula are the calcium carbonate, which is CaCO3, and the phosphoric acid, which is H3PO4. And these create the products tricalcium phosphate, Ca3PO42, carbon dioxide, and water. And a similar thing happens at the Pedro Banks, only this time the droppings come from birds. The Mineral Resources of Jamaica goes on further to say, and I quote, some of the largest deposits accumulated in caves developed where the coastal platform or coastal plain abuts against the limestone hill, as for instance in the Portland Ridge of Clarendon. Within the interior, the main concentration of caves is in the deeply dissected cockpit country, which is difficult to access, and it is possible that much more phosphate occurs in this area than has so far been reported. End quote. We'll talk about the caves in Jamaica in future episodes. Anyway, what I want you to take from this segment is minerals with PO4 in their chemistry fall in the phosphate group. All right, so sulfides and sulfates now. The spelling will vary based on where in the world they're from. I will try to keep it as simple as possible here. Sulfate minerals contains sulfur and oxygen and usually form near the Earth's surface in places like dried up lakes. They're often soft, light colored, and used in things like plaster and drilling. Examples include gypsum and barite. Sulfide minerals, on the other hand, have sulfur without oxygen and form deep underground where there's little oxygen. They often look metallic and are important sources of metals like lead, copper, zinc, and so on. Common examples are galena, pyrite, chalcopyrite, and that's quite simple and straightforward. That's it. So now we're at the oxides. Oxide minerals form when the element oxygen bonds with metals. Some of Earth's most important metals, which we use every day, started in this way. And this includes things like iron, uranium, and titanium. So native elements are simple, no bells and whistles, no bonding. They are simply just a pure element in free state in nature. Think of gold, for example. You often hear people panning for gold in rivers. Pure silver also occurs in nature, and so does pure copper. The thing about these three elements, gold, silver, and copper, is that they often occur together in nature, often in hydrothermal fluids. And we will discuss this in our next episode. But anyway, another native element which the uninitiated may find surprising is diamond. And why is diamond considered a native element, you may ask? Well, diamond is pure carbon, and that's pretty much native elements. So evaporites are classified according to how they form rather than their composition. There are two major processes at work here. Now, I want you to think of or imagine two things. I want you to think about a climate that is very hot and dry, semi-arid to arid. I also want you to think about a body of water like a lake or pond. Okay, cool. So here's what happens. Water accumulates in a shallow lake or sea or lagoon. This water has dissolved ions like calcium, sodium, chloride, and sulfate. High amounts of evaporation occurs due to the hot climate, and I guess you can see the connection now. They are called evaporites because of the process of evaporation. As the water evaporates, minerals are left behind, and in science we say the minerals precipitate out. If calcium is present, calcite precipitates out first, followed by gypsum, then anhydrite as gypsum loses water, and finally halite. And that is pretty much how the process works. So the key takeaway from this segment is that evaporites are formed in areas of high evaporation. As the water evaporates, the minerals are left behind, and common minerals are halite, gypsum, and anhydrite. Before we move on, just a quick note on Jamaica. One of the most common evaporite minerals in Jamaica for a very long time has been gypsum. And if it is one of the main ingredients in Carib cement. The largest deposits of gypsum on the island occur in and around Bull Bay, and you can kind of see why. Bull Bay in St. Thomas is very hot and dry, kind of like a lot of the South Coast in Jamaica, really. I mean, if you check the levels, many places along the South Coast facilitate vegetation which thrive in dry conditions. If you look at areas like Bull Bay, like I just mentioned, Palisadoes headed to the airport and Port Royal, South Clarendon like Rocky Point and Milk River, Hellshire in Portmore, lots of dry vegetation like the cactus and a thorny local plant known as kashamaka occur in these areas, sometimes in abundance, which is evidence of a historically dry climate. Anyway, my point is Bull Bay is very hot and very dry historically, and the high evaporation plus the right geological conditions led to the formation of gypsum, which we use in our cement today. To think of that is just quite amazing and fascinating, and it's so cool. I think most people like gemstones. They are shiny, they're eye-catching, and quite beautiful. And if you are a person that's really into fashion, you probably say that no outfit is complete without a piece of jewelry containing a gemstone. From engagement rings to earrings to the pendant on your favorite necklace, gemstones appear everywhere in the jewelry and fashion industry. But what are they? Well, the Oxford Dictionary of Geology and Earth Sciences define gemstones as naturally occurring mineral that has been artificially polished, faceted, and shaped for decorative purposes. There are two general categories of gemstones. We have precious gems and semi-precious gems. The differences between them are based on tradition and market value and not a scientific classification in the strictest sense. Gems are considered precious based on their rarity or perceived rarity, uh, their exceptional hardness, high clarity, fire, and brilliance, as well as the market demand. The four most common precious gemstones are diamond, of course, ruby, sapphire, and emeralds. Before I get into the semi precious, I think it is important that I say please do not let the term fool you. Semi precious minerals too are very valuable, and in some cases, semi precious gems can fetch more than precious gems. One example would be a high quality opal fetching more than a low quality ruby. Uh, a lot of this is based on perceived value and people's likes and preferences. I must also add that during my research for this video, I found that in some cases, people don't even like to use the term precious and semi-precious anymore, as it can sometimes create confusion and what I like to call gemstone discrimination. That's my little word. But anyway, this isn't a large demographic, and precious and semi-precious are still widely used terms. I will provide a summary graphic on screen here, but precious gems include diamond, ruby, sapphire, and emerald, and semi-precious include amethyst, garnet, opal, topaz, and jasper. Now, as a student of geology, I learned mostly about the classification of minerals based on chemical composition and how they formed. In industry, I learned that the classification was based on end use. I learned that there are two broad categories in industry. There's industrial minerals and metallic minerals. Industrial minerals, you know, it's any earth material of economic importance, which excludes metals and fuels. In the Jamaican context, think of limestone, sand and gravel, clay, gypsum, alabaster, that sort of stuff. Lots of these minerals are used in construction, paints, cements, artwork, and pottery. Metallic minerals are self-explanatory. They're metals. Examples include galena, which is a source of lead, malachite, a copper-bearing mineral, and hematite, an iron ore. Most of the metals I discussed earlier, like oxides, sulfides, and native elements, are metallic minerals. So, why does classifying minerals matter? First off, minerals are the building blocks of rocks, right? And rocks tell the story of Earth's history. By knowing what minerals are present in a rock, we can figure out how and where it formed. For example, the limestone in Jamaica are packed with a mineral called calcite. That tells us that the island was once under a shallow sea. Amazing, right? But it's not just about the past. Classifying minerals also helps us to understand things in our everyday lives. Different groups of minerals serve different purposes. Silicates, well, they're used in glass, ceramics, and even electronics. Carbonates, that's your cement and building materials. And sulfides, they give us metals like copper and lead. Even in Jamaica's bauxite, the source of aluminum, it belongs to a special group of oxide minerals. Knowing the classification helps industries explore for resources, mine them efficiently, and use them safely. And speaking of safety, Some minerals are dangerous. Asbestos, for example, belongs to a group of silicate minerals that can harm your lungs. Sulfide minerals, when exposed to water and air, can cause acid mine drainage that pollutes rivers and soils. And by understanding what mineral we're dealing with, we can manage risks and protect the environment. So classification isn't just about putting labels on minerals. It's about unlocking stories, guiding exploration, powering industries, and staying safe. That's why we classify minerals. So this marks the end of this episode. We covered mineral classification quite extensively, and so far in the series, we have really delved into minerals. In our previous episode, we learned what minerals are and how to identify them. Today, we learned how to classify them. In our next episode in the series, we are still on minerals. This is the last, that will be the last mineral episode in the series. We will explore how different minerals form. Drop me a comment. Let me know what you found the most interesting about this episode and how you are enjoying the series so far after 5 episodes. So take care and I will see you next time. Bye.